Hello and welcome. Today, we're diving into a fascinating field that could reshape the future of computing and artificial intelligence: neuromorphic computing. What is it? Essentially, it's about building computers inspired directly by the structure and function of the human brain. Think about today's computers. They follow what's called the von Neumann architecture, where the processor and memory are separate. Data constantly shuttles back and forth, creating bottlenecks and using a lot of energy. This is especially true for the massive AI models we see today, which are incredibly power-hungry. Neuromorphic computing offers a different path. It tries to mimic the brain's incredible efficiency by putting processing and memory much closer together, sometimes even combining them, just like neurons and synapses in our heads. This reduces data movement and saves power. A key element here is the use of spiking neural networks, or SNNs. These are different from the artificial neural networks, or ANNs, commonly used in deep learning. Instead of processing continuous numbers, SNNs communicate using discrete pulses or spikes, much like biological neurons. They are often event-driven, meaning they only compute when a spike arrives. Imagine a system that only wakes up to process relevant information. This leads to potentially huge energy savings, especially for tasks that require constant monitoring but don't always have a lot happening, like a security camera or a wearable health sensor. Plus, the timing of these spikes becomes part of the computation itself. Hardware is where things get really interesting. Companies like Intel, IBM, and BrainChip, along with research institutions, are developing specialized neuromorphic chips. We have Intel's Loihi 2, IBM's North Pole, and BrainChip's Akita, plus research platforms like Spinnaker. These chips use various approaches. Some use analog circuits to closely mimic neuron behavior, others use digital for precision, and some mix the two. Researchers are even exploring new materials like memristors, which can act like artificial synapses, changing their connection strength based on activity, allowing the chip itself to learn. The core idea is massive parallelism, lots of simple processing units working together, just like the brain. So why go through all this trouble? The biggest driver is efficiency. Neuromorphic systems promise to perform complex AI tasks using potentially orders of magnitude less power than traditional hardware like GPUs. This is a game changer for devices that run on batteries. Think edge computing, smart sensors, autonomous drones, or even advanced prosthetic limbs. They also excel at real-time processing due to their inherent parallelism and low latency, crucial for applications where quick decisions are needed. Another exciting aspect is on-chip learning. These systems can potentially learn and adapt continuously from new data directly on the hardware, using principles like spike timing-dependent plasticity, without needing constant retraining in the cloud. Of course, it's not all smooth sailing. Developing the software and algorithms to effectively program and train these SNNs is a major challenge. We need new training methods and user-friendly frameworks to unlock the hardware's potential. Thankfully, tools like Lava, Nest, and Nengo are emerging to help researchers build and deploy applications. And the potential applications are widespread. We're talking about smarter, low-power devices for the Internet of Things, more efficient robots and self-driving cars, advanced sensory processing like artificial retinas, real-time medical diagnostics, powerful tools for neuroscience research, and even novel cybersecurity systems. However, neuromorphic computing is still very much an emerging field. Challenges remain, like scaling these systems up to handle truly brain-like complexity, ensuring high accuracy, creating industry standards and benchmarks, developing algorithms that fully exploit the hardware, and integrating these new systems with existing computers. It's a complex, interdisciplinary effort. Looking ahead, the future points towards more capable neuromorphic systems, perhaps even hybrid approaches, that combine the strengths of brain-inspired computing with traditional deep learning. The ultimate goal is to create AI that isn't just powerful, but also energy efficient, adaptable, and capable of learning on its own, paving the way for truly intelligent systems that can be deployed almost anywhere. It's a field to watch closely as it continues to evolve.